Hello, Year 10. Mr. Harrington here again. And what my plan is to work through lesson 10A6 on waves and sound, continuing in the topic on light and sound. Now, this is a little bit of a recap, so you'll have come across some of these ideas in Year 9. So, if you think you've done it before, then you have. But these are really important foundational ideas that almost certainly will be tested, either longitudinal waves, transverse waves, or wave shape and their application on your exam. So let's go through it anyway. So first of all, there are two types of wave that you need to know about. There are actually more types of wave than this, but for the GCSE syllabus, just longitudinal, transverse is what you need to know about. So longitudinal waves are waves where the vibrations or the oscillations that basically form the wave are parallel to the direction of travel. Okay, so you need to learn this description. It would need to be something that you would need to memorize. Okay, so super important. Let me put it in a green box. Yeah, important. Okay, so what I'm trying to show you here with this diagram is the actual propagation of a longitudinal type wave. Now that's difficult to see. I do have a little computer video animation thing over here in a moment that I'll show you, so perhaps it will make it clearer, but I am including this diagram and discussing it deliberately because this is often the way it's portrayed in revision guides and in exam questions. So we've got these little orange lines, vertical lines, and they represent particles in the material where the wave is traveling. Okay, so there's my arrow. Direction of wave is from left to right. And what we're showing here is the vibrations themselves are going from left to right as the wave travels along. Okay, so remember, waves transmit energy. They don't transmit material. So we don't get material atoms moved here to the right, but you do get energy moved here to the right. A couple of key features. If you have regions, therefore, if these vertical lines represent the atoms, you can see here they're clustered closer together, here as well, and here as well. Okay, so those are known as compressions, a term that you would need to know. So sometimes I've seen this on exam and you're asked to label where the compressions are, or indeed the opposite to where they are compressed together must mean atoms are pulled from there, creating these spaces. So you get a region, here and here and here, where the atoms therefore are stretched further apart, and those are known as rarefactions. It's an odd word. You don't see it anywhere else ever that I've ever seen other than this diagram. So these are known as rarefactions. You do need to know that term. RAREFACTIONS. And it comes from a bit, if you understand the word rare, it means there aren't very many of something. And so there aren't very many atoms or the particles that are transmitting the waves in these particular three regions, hence rarefactions. Okay. So, I'll go through the computer in a moment. Let's just talk about transverse waves. Okay. So the other type of wave you need to know about is known as the transverse wave. And transverse waves are where the vibrations or oscillations, you can see here, are perpendicular or transverse. That means the same thing, perpendicular or right angles to the direction of travel. E.g., waves on a string, electromagnetic waves like light and infrared and ultraviolet, and so on. Okay. I do just remember I didn't specifically mention the examples there. So examples of a longitudinal wave are sound waves or pressure waves. Okay. So back to transverse. So remember, the difference between transverse and your longitudinal primarily is the vibrations now. Can you see they're up and down in this diagram? And yet the wave is traveling this way, it would be represented as. Okay, so the vibrations are like this as they travel along. Again, if I show you a computer demonstration of that in a second, perhaps it'll be easier to see. So if you just bear with me a moment while I shuffle about my two laptops and see if we can get this working in a reasonable fashion. Sorry, I'm just thinking, what's the optimal way of doing this? No, That's going to now be upside down, isn't it? And left to right. Aha! Well, that's pretty much as good as we get. Okay, that's okay though. So here what I've got on the screen, scrolling away, is this demonstration of a longitudinal wave. So both of these are longitudinal waves. They're just trying to emphasize different features. So if you look carefully at these representations, if you look carefully in there, there's a little red particle that you can see is just moving left to right. There is to the right and to the left. And so they've just highlighted a particular one so that you can concentrate in on that. Now, if you look at any of these carefully over time, you will see that they are every particle is only moving left and right. However, if you look sort of zoom out a little bit, you can see this kind of larger scale behavior where you can see these wave fronts that are progressing left to right. And if I just follow one along here, we get this region of compression where the particles are squashed closer together, but that compressed region is moving along, but the atoms themselves aren't. It's just a pattern within the atoms that is moving. So energy, or indeed information, could be transmitted along, because that's sound waves. So when I'm talking at the moment, there's a pattern of compressions and rarefactions that are coming from my mouth. They are traveling through the air like this to the microphone on my camera, in fact, microphone on my headset, and recording the sound, okay? But there is no particular air moving from one place to another. And you can see that on this one here. It identifies a particular particle, and there's an arrow that follows along a wave front, okay? And it also mentions here about the compressions and rarefactions as it's traveling along. Okay, so that's the longitudinal wave. And if I scroll down here, there is an example of the transverse wave. So again, if you were to look at any individual atom, all it's doing is moving up and down. However, you can see an overall, hopefully you can see this picture of a picture, overall pattern of waves moving from left to right. Now, if I have any sense, actually, where it's just come to me while I'm filming this video, if I make a note of the website address and include that within whatever instructions I have with this lesson, that would be a good idea. Okay, so moving onwards, let's get that out of the way and try and find my next relevant sheet of paper while I smash the place up a bit. Try not to slop my coffee about. Where are we? So we're on to my second page here. So that was all really a bit of a recap, but it is information that you need, and hopefully you're able to, pause your video at various points to be able to make any notes that you need. So the next key thing is being able to identify key features on a wave. So I'm calling that wave shape. And you can see here I've drawn an axis of displacement against time. Now, if you're unfamiliar with the term displacement, you should have covered that in year 9, but don't worry about it for the moment. If you like, you can just think of it as distance. So imagine this is, I don't know, this could just be a single particle oscillating back and forth, and we're drawing a graph of time as it oscillates back and forth. Now, you need to be able to read off certain key features from a graph of a wave and understand what they mean. And the most common way that we do this is displacement or distance against time. However, these graph axes could be different. This could be voltage against time, or current against time, or it could be displacement against displacement. Okay, so it could be how far you're displacing up and down, but also as you go along the wave. So the wave could physically look like this in real life. If I did a wave on a guitar string, so I pluck the guitar string, it would have this wave pattern along the length of the guitar string. Now, normally here, the height of the wave is so small on the guitar string, it's very hard to see unless you're looking super carefully, maybe taking a video and slowing it down, that kind of thing. Anyway, so back to what you specifically need to know. You need to know what the wavelength of a wave is. Now, the wavelength of a wave, and I've defined these below in a moment, is the distance between two key features of the wave, okay, two repeating key features. So here I've got 2 peaks. So that distance there to there between the 2 peaks is known as the wavelength, and it has the symbol, the Greek letter lambda. Okay, now that looks like an upside down Y, just in case people get confused. There's a little white gap there. Let's get rid of that. So it's like a capital Y upside down, and it's pronounced, can you see here, lambda? And that's the symbol for wavelength. So distance between 2 peaks, it could be, you can see here I've denoted it, the distance between 2 troughs. It could also be, say, the distance between where it crosses this line at 0 and is traveling upwards. So the distance between this point and this point could be the wavelength. Because sometimes I've seen these on exam questions where you don't have 2 peaks, you only have 2 troughs. And I've seen students go, I don't know how to do it, because you can only see 1 peak. And as well as the distance between 2 troughs as well. The other key feature that you need from this is to know the thing called amplitude, given the symbol capital A. And that is the distance from this line at 0 and the maximum. Okay, so how far, this we sometimes call it the equilibrium position. So how far a wave at its furthest point can move, can displace from the equilibrium position at 0. So it could be from 0 to a peak, it could be from 0 to a trough. So that distance there is also known as an amplitude. Okay. Now I'm just going to show you this little thing here, because this came up on an exam question one year and students did it very, very badly. So I know we as a department, we put it in the end of year exam, I believe, for year 10 and in the mocks a couple of times, just to try and get the point across. So there was a question in exam that showed you a little diagram like this. It had this distance from the height of a peak to the depth of a trough, and it labeled it X and said, what does X represent? Okay, and students got themselves tied in knots and couldn't get it right. I mean, a handful did. So if we look at this distance here to here, that is the amplitude. Okay, and this distance here to here would also, as I stated, be an amplitude. And therefore, if we go from the top all the way to the bottom, it is 1 amplitude plus 2 amplitudes. So 2A, okay, represents 2 amplitudes. And a lot of students, when I pointed this out, said, well, I thought it was that, but it, I didn't feel confident to put it down. Anyway, I've shown it to you now. Anyway, here are a whole load of key terms. You might want to pause the video at this point and make sure that you've got appropriate notes on these. So we've got wavelength, as I said, is the distance between 2 similar features on a wave, e.g. the distance between 2 peaks or 2 troughs. The unit is measured in meters, or it could be, as I was saying, a number of other units, depending on what's displayed on the graph. But commonly, distance could be time as well. So A equals amplitude, and that is the maximum extent of an oscillation or vibration from the equilibrium position, and the unit is, I've got here, meters, although it could be a graph of voltage. And I believe in a lesson or two I'm going to be showing you a voltage graph and how to read an oscilloscope, so we'll be looking at that, where the amplitude is actually a voltage. T equals the time period, and that's the time taken for one complete oscillation or vibration. Okay. Or on some types of graph, if you've got a graph like this of time, and again, I'll show you this on the oscilloscope in a coming lesson, then actually the distance between the 2 peaks here, if it is time this way, then that's going to be the time period as well. So the wavelength would be the time period. Yeah, it's getting confusing. Don't worry, you'll get the hang of it once you've done a bit of question practice and revised at the end of the year and, gone through some your mocks and prepared there. You will get the hang of it. It will make sense as long as you keep working and asking questions when you're stuck. Anyway, final one, F equals frequency, and that is how many complete oscillations you get in a second, and the unit is hertz. Okay, one more last little thing. There is an equation that you maybe have seen before that's important here, and that is the time period equals 1 over the frequency. So I've just defined those previously, so I'm not going to define them again. So if you rearrange that, that's also equal to frequency equals 1 over time period. So here's an example. Mains electricity in the United Kingdom has a frequency of 50 hertz. What is the time period? Okay, so time period equals 1 over frequency equals 1 over 50 equals 0.02 seconds. And hopefully I'll be showing you a demonstration where we'll be looking to test this idea about the UK mains frequency in a coming video. But that's this video done. Thanks very much. Mr. Harrington signing off.